Oh, yeah, I think I'm online. Hello, everyone. After this great workshop of Benjamin, I'm now presenting a tunnel boring simulation model. Thanks a lot for everyone here from the AnyLogic team that I can present today. So for the start, I think everyone knows these big construction sites in town. They are loud, noisy, make the traffic even worse, and it seems that they will never end. So what I'm presenting today is an approach to make these construction sites in inner cities better, at least for the construction sites for building tunnels. And with that, welcome to my presentation on process simulation and mechanized tunneling. This case study is about optimizing a construction site for a tunnel drive with a tunnel boring machine in an inner city area. Here, laser pointer is not on, sorry. So laser pointer's on. Here you can already see a 3D representation of an agent, but more about this later in some video clips. The optimization approach I'm about to present was developed within the Collaborative Research Center, SFB 837. Here you can see the 4 main projects of the SFB. The goal here, my process simulation is located in the sub-project C, and the goal is the analysis and management of tunneling processes by using modular process simulation models. The sub-project leader are Professor Markus König and Professor Markus Teves. In order to be able to describe the optimization with simulation models dealt with here, I would like to briefly say something about mechanized tunneling. At the bottom right, you see a picture of a tunnel boring machine, in short TBM. To be precise, this picture represents a slurry-filled machine, but I don't want to go into detail in different types of TBMs. As a rule, there are always 2 alternating core processes that are indispensable for mechanized tunneling. Firstly, the cutting wheel in front rotates and thus removes soil. On the other hand, the tunnel safety lining must be installed and the protection of the TBM shield. So here's the TBM shield, and here's the tunnel lining. Here in the tunnel lining, you can see that one wing always exists of several elements. In this project, one wing consists of 6 elements. Both processes, so the excavation and the building of the wing, alternate in most machine types. So either the TBM is excavating or the tunnel lining elements are installed by the erector. There are many processes that are also required for tunneling. This results in a large number of machine components and logistical elements without which the tunneling cannot take place. The failure of one element can often result in the TBM coming to a standstill. There are various logistical challenges that arise that can be analyzed using process simulation. For example, the storage areas for all the required materials are limited both at the machine and at the construction site located above ground. In addition, the transport distance from the above ground construction site to the current point of the TBM increases as the excavation of the tunnel progresses. So why are process simulation used in tunnel construction? In general, the tunnel construction time is to be reduced. For this purpose, various logistic processes of mechanized tunneling were analyzed in different models. The driving performance is not solely dependent on the 2 core processes of wing construction and excavation. The achievable performance depends on many other support processes. Therefore, a conventional calculation of the tunneling time is only possible to a limited extent. Extensive analysis of the advanced and support processes with the aid of process simulation are intended to reduce the downtimes. The aim is thus to achieve robust planning of the logistics and maintenance processes that also takes into account uncertainties, especially in the input data. Since optimization should always be carried out with as few variables as possible, different areas of tunneling are optimized in different models. In the optimization approach I am about to present, the above-ground construction site is to be optimized. Inner city constraints, such as noise regulations, traffic congestion, and environmental compatibility, are to be taken into account. The goal was to keep the occupied area as well as the tunnel construction time as low as possible. In addition, the model is to be used to examine the extent to which process simulation can be usefully employed in the early planning phase of mechanized tunnel construction projects. The two key processes at the surface construction site are the supply of segments and the disposal of soil. It is precisely these two logistic processes that were focused on in this case study. On the left, the segment transport by truck is shown. As a rule, a truck can transport one wing, so in this case study, 6 elements. On the right, you can see an example of how the excavated soil is stored in separate heaps. Each heap is sampled individually. After a certain analysis period, the material is then disposed of. As already briefly mentioned, variations in the logistic processes were simulated in various models. One variation were the means of transport for supply and disposal. So here on the left side, you can also see a picture of how the segments are delivered by train to the construction site. The same can be done for the MAC, of course. So now to the model. Here you can see the basic structure of the required model. The model is divided into 4 main agents: 2 tunnels, the soil disposal or the MAX system, and the local construction site. There's also an agent to track the simulation progress, but this is only for easier validation. So in this case study, there are 2 tunnels that are being excavated simultaneously. Because there are 2 trains switching in the shaft and switching and supplying the TBM, there are all in all 4 trains for both tunnels. The model should be very simplified in the tunnel agents because I am focused on the upper side, so on the above ground construction side. Therefore, only the trains responsible for supplying the TBM and the TBM itself are included in these agents. All tunneling and support processes are combined in a highly simplified way in the TBM agent. In the MAX system agent, the MAX storage is to be simulated in detail with all the accompanying processes, including a separation plant. And the local construction side is mainly to simulate the segment storage in detail. But I don't want to go into detail about all the agents. But on the basis of this model description, how did we try to optimize the construction site? Again, the goal was to keep the storage areas as small as possible without restricting the tunneling process too much. To try out different logistic variations, 11 simulation models were created, in each of which a small detail was modified. From the analysis of all the model variations, one optimized simulation model was created. In this way, it was possible to optimize the logistic process of mechanized tunneling, taking into account a lot of inner city boundary conditions. So here in red, I marked the agents that have been modified slightly for each model variations. The means of transport used to dispose the MAC or to deliver the segments was varied. In the initial model, trucks were used, and in different variations, the means of transport for supply and disposal were changed to trains. In addition, the arrival times or the frequency of the arriving vehicles were varied. In other variations, the size of the segment storage and the amount of heaps in the MAX storage were varied. For those parameters, we also used the possibility in AnyLogic to analyze the model variation with sensitivity analysis. As briefly mentioned earlier, the soil must be stored for soil analysis. After about 14 days, you get the results of the soil analysis. With that, you can decide where the soil has to be disposed. If you pay more money for the analysis, the period can be less than 14 days. If the max storage is full, that could be a good idea. So the downtime of the TBM, because the excavated soil can't be stored anymore, can be much more expensive than paying a bit more for the soil analysis. So this sampling period was also varied in another model variation. Last but not least, for the local site setup, the crane type was changed in a model variation from a gantry crane to a tower crane to evaluate the impact on the logistic processes. So in order to model this model structure, a software is needed that allows multi-model model creation. It must be possible to implement both the intrinsic behavior of each agent and an interaction between the individual agents. Also, in the machine tunneling, it is necessary to integrate fluid flows. In addition, I personally like the simple 2D and 3D model representations in AnyLogic. This greatly simplifies the verification and validation of the models. So then I will move on to a couple of videos showing the created simulations of the segment logistics and the MAX system. First of all, the local construction site. That is the segment storage here in blue with the truck delivery at the site and a crane transport here in the 3D representation you see in the gantry crane. In the shaft, there are 2 tunnels. You only see 1 tunnel, but there are also 2 trains, but each train here is for 1 tunnel and each tunnel has 2 trains. Above the presentation, you can see 3 different flowcharts and some variables, parameters, functions, and stuff like that. Some words are here in German, but the parts I want to explain to you are in English, so you can ignore the rest. The long flowchart here is for the movements of the crane. There are also distribution functions for various parameters in the model. For example, the crane failure was considered with a distribution function. In a Monte Carlo simulation, the frequency of a crane failure therefore varies for each simulation run. And we have here on the right the flowchart for the arriving trucks with 6 segments, with 6 segment elements, so 1 wing. And the last flowchart implements a bucket of mortar that has to be delivered by the trains through the tunnel to the TBM as well. Oh, then I will start the video. Here we switch directly to the 3D view. And you see directly on the left a truck arriving with 6 segments. The gantry crane starts to transfer the segments to the segment storage. For this purpose, it must drive back and forth twice, because it only can carry 3 elements at a time. And the same procedure is carried out for the train. And after loading all the segments, there's also a bucket of mortar that is transported to the train. So here's one model variation. Instead of a gantry crane, a tower crane is used on the local construction site. You can see immediately that the tower crane takes up more space, thus reducing the size of the segment storage. In addition, the tower crane has a lower weight capacity than the gantry crane. Thus, only 2 segments can be transported at a time. So unloading or loading for 1 wing takes 3 crane cycles. So now I'll show some videos of the MAX system. Here you can see the individual heaps represented in rectangles. Green heaps are free heaps. The bright blue rectangles that has also some smaller elements on it are heaps that are being filled at the moment. The black marked heaps are deactivated in this model variation. The number of heaps are parameterized so that sensitivity analysis can be performed. In this way, the influence on the construction time with different numbers of heaps could be understood directly. At the top of the video, the result of the soil separation plant is shown as 3 tanks. The separation plant sorts the soil according to grain size. In this case study, there is coarse, medium fine, and fine soil. each soil has its own color for simplified validation. So each soil is stored in its own heap. At the top left, so here, you can always see two different heaps on a light blue background. And on every heap is another color of elements, another element with another color. So there's another thing I want to mention. Here are forklifts, but they shall represent wheel loaders. So yeah, I start the video and you can see the wheel loader get the soil from the tanks of the separation plant and brings it to the heap. I forgot to mention, each element that comes from the separation plant has the volume of one wheel loader shovel. Of course, just in this simulation model and not in reality. Afterwards, the wheel loader transports the soil. Yeah, okay. The wheel loader transports the soil to the heaps with the same soil type. Okay, and I'm getting to the next video. Don't be alarmed, it gets more colorful. Here you can see many red and orange rectangles. The wet heaps are full heaps that will be sampled before disposal. Only when the analysis result is available, it is clear where the soil will be disposed of. So the disposal of the orange heaps has already been decided. In this video, you can now see how the wheel loader gets to one heap where it is decided where the soil has to be disposed of, gets one shovel of soil and brings it to the truck that stands ready to get disposed of the soil. Yeah. So now I would like to summarize the advantages of this optimization approach. I will briefly summarize how the procedure went. An initial model was created. Parameters to be planned, such as the storage sizes, were determined in a conservative way. Expert interviews were conducted with various tunnel construction planners as a basis. After that, small variations were made to the model in many individual models. Each variation was evaluated with respect to the tunnel construction and downtime and the inner city boundary conditions. Inner city boundaries would be something like the number of trucks approaching the construction site every day. Based on the analysis of the model variations, an optimized model was created which is suitable for the inner city boundary conditions and enables the shortest possible construction time. Finally, in the optimized model, so this one, the disposal of the muck was implemented with trains instead of trucks, and the size of the storages was increased minimally. In this diagram, you can see two histograms for the tunnel construction times achieved in a Monte Carlo simulation with 1,000 repetitions per model. So here at the right, the initial model, and on the left, the optimized model. So here in the left-hand pie chart, it is shown once again, the total construction time is made up of the two core processes of excavation and wing building, as well as the downtime. You can now see that the downtime is much less in the optimized model than in the initial model. The right-hand pie chart shows the various reasons for tunneling downtime. So on the next slide, the improvements of the optimized model are summarized once again. So just shortly here, the tunnel construction time of the initial model is with 194 days in average and 169 days with the optimized model. I think there will be a lot of questions. I will come into that later. The reduction of the total tunnel construction time is 25 days on average. This is mainly achieved by reducing the downtime by 40.5%. This made it possible to achieve an advance rate of 17.8 meters per day. In contrast, only an average advance rate of 15.5 meters per day could be achieved with the initial model due to the high downtimes. But to the additionally important part in this project, the inner city boundaries. The number of trucks, for example, approaching the construction site every hour, has been reduced from 8 to 2 to 3 trucks. On a daily basis, this equals 70 fewer trucks impacting the inner city traffic. The reduction in traffic load was mainly achieved, of course, by changing the disposal of the soil material via train transport. And what do all these developments mean for the application of mechanized tunneling? With the approach developed here, it is possible to compare different variations of logistic already in an early planning phase. Because of the possibility to consider uncertainties in the process simulation, AnyLogic is perfectly suited to be used in the early planning phase for designing the logistic processes. Also within the scope of the special research area at the Ruhr University Bochum, research is also being conducted into the extent to which process simulation can be applied during the execution phase of a tunneling project. Here it is worth mentioning that it is possible to do construction site controlling with the help of a digital model. In the case of incidents, it is also directly possible to compare different variants of reacting to the incident with the process simulation first. Since a model that has already been created can be modified relatively quickly in AnyLogic, there's a great deal to be made for applying process simulation in the execution phase of mechanized tunneling as well. And now to the last slide. The initial model for this project was created using, among other things, the early planning data of the U5 Mitte project in Hamburg. For this, there was very close cooperation with the Schüssler Plan engineering company. The created model could therefore be applied in the further planning of the U5 Mitte. Also, in the execution phase, validation and close exchange with Schüssler Plan is planned. So thank you for your attention. I will now go to the questions. I think there are some. Let me have a look at it. Yeah, so Louis is asking if you can use the model for decision making in the sampling period. Well, in the sampling period, we don't have to make any more decisions because the analytic, so the result of the analytic, will say us where to get disposed of the soil. So at the moment of the analytic period, we can't decide where the soil is going. But we can use the model to decide if we have to pay more for the analytic period, so it's getting less long, because maybe if we already have a lot of heaps that are full, maybe it's important to reduce the analytic time and then get earlier free heaps. So yeah, it would be possible to use the model for decision making on that. And from Abadi, the question, what type of simulation model have you applied? So it was a modular simulation model. So I used agents and everything. I really used everything that is possible to use with AnyLogic. And then, how was the data collected? Yeah, I think I came to that a bit later. So the data was collected of a lot of research that has been done in the special research area of the Ruhr University Bochum. And also with some expert interviews with 4 or 5, I don't know, I don't remember, tunnel construction planners. So all the input data was from some different projects that has been done in the research project and from construction planners from the reality, from the real construction planners. Wow, really a lot of questions. I have 5 more minutes. I hope I can get through everyone. Okay, I think the question is from Mohammad, can we merge a group of individual models to be one system? Well, I didn't make a lot of different models. I just made one model, and in model variations, I just changed small bits of the model. So I can't say something to that. Sorry. No, yeah. So Gavin asked if it's possible to say what kind of financial benefits resulted. No, not yet, because when I started this project, it was a really, really early planning stage of the U5 Mitte in Hamburg. So we didn't have a lot of data for the financial things. So I couldn't get a financial benefit into the simulation model. But that's definitely a point I want to do in my next research. So more questions. Yeah, there was another question. How did you validate the model? Yes, how did you validate a model? I think that's a really, really difficult question. Well, I went through the model a lot of times. I looked at the representations, of course, but always the representation can also have faults, though it's not the only way to validate the model. The best way to validate the model would be with a real project, and that will come. So the real verification will maybe be a bit later, but of course, all the other verification and validation possibilities, like going through it and calculate a bit of the model yourself, so by hand, and then control if it's the same in the model. Of course, I did all of this. So yes, and everything else will be maybe in a real project of the U5 Mitte. So 3 minutes left. How did you implement regional construction policies in the model? That's another difficult question. So it was difficult to implement it in the model. The only way was to compare it with your own mind. So it was not definitely in the model. Like noise, I couldn't implement noise regulations with AnyLogic, or at least I didn't know how. Maybe it's possible. Other things like the traffic, of course, I could get some values out of the model. So how many trucks are coming to the construction site and stuff like that. So I could see difference between the models. So how many trucks are coming in model variation 1 and how many trucks are coming in model variation 2 and stuff like that. So I could compare that. And other policies like the used area of the construction site was of course possible because I changed the number of heaps on max storage, and I also changed the number of storable segments. So with that, I could compare, is it possible to get an area in a town like Hamburg that is big enough to store so many segments and so many heaps of muck. So I think that were all questions. So thank you very much for your attention. And yeah, I hope the rest of the presentations are really interesting. I'm looking forward to it.
Okay, yeah, thank you, Judith. Thank you so much for your really great presentation. And